All right. Oh, whoop. Let's try that again. Lecture 27. Let's get the lights adjusted. That homework was bad, wasn't it?
Yeah.
I told you it was a long one. But hey, I mean this. That was the hardest homework whole semester. Hardest one. I mean it. For example, when we do influence lines, those homeworks are really fast. They might be like a little tricky, but they are fast. They're very fast assignments.
It would be hard. Just the second problem had so many sections. You just had to be.
Yeah, and the thing is, I mean, if you understand that, then you understand how to do really any problem. And I will go ahead and tell you that that was a challenge. The exam won't be that bad. You'll see what I mean. Okay. I am still working on your project submittal one. My apologies. But I'll say this. Really, the time critical aspect on the project is that I get it back to you by the time that we start mass hand. Because you really can't start submittal 2 until mass hand. Because that's what submittal 2 is all about. So that's not going to be till after the second exam. So like I want to get it off my desk, but as long as I get it done by the mass hand exercise, we're good. Okay. Today is our last exam 2 topic, is frame deflections. This is it for what's covered on exam 2. So Friday we review, Monday we celebrate, okay? And next Wednesday, no class. No class, and I'm not going to pre-record anything. Not going to give you an assignment while we're gone. Just peace, if that's okay. Did you all get my email about homework 6.3? I forgot to mention that in class on Monday, and I think it was because my announcement slide hadn't synced up. But I posted a homework that all you have to do is install Masthand. Install Masthand, upload a screenshot of it running, full credit. I'm doing that so that when we come back after the exam, I've had this happen before where, well, I never installed it, and then we're sitting there in class trying to get it installed. It's a really, really quick assignment. Okay, everybody good? Okay, let's get into frame deflections. This is our last topic on exam 2. And I want to start with this, which is what we're all familiar with at this point, right? This is the method of virtual work for beams. Everybody knows how to do it, but what I want to do is I maybe want to see if there's some patterns to this. For example, what we're doing here is we're saying, okay, the deflection, and we'll call it deflection flexural, is, okay, so we're summing up some stuff. What are we summing? We're summing up a series of integrals. Okay, what are in these integrals? Okay, there's some fractions. Okay, and what goes in these fractions? Okay, so we have EI and we have MM. Okay, so let's see if we can, generalize this a little bit. What we have here in this fraction, this right here, that's a material property, right? Right, E is what you get from a material test, right? Go do a tension test on a piece of steel or something. Okay, what is I? I is a section property, right? That's a characteristic of the shape of the beam, right? Okay, and then we have a real analysis, and then we have a virtual analysis. And that's basically the pattern for virtual work. Am I right? Okay. So we talked about this at one point. We said, well, what about if we were doing axial? Okay. One way that we could write axial deflections is we could say, okay, we're going to sum these up. Now, in trusses, we didn't integrate them. But if we did integrate them, we would have a bunch of integrals. And what would the integrals be? It'd be little f, big F, E, and A, right? And if everything's constant and we integrate dx, we get an integral from 0 to L, and we get little f big F L over EA, which is what we did use for trusses, right? So what does this look like? Well, on the top, what do we have? A virtual analysis, a real analysis, we have a material property, and we have a section property. So couldn't we, like, go through this the whole way? I mean, like, for example, what if we wanted to do a delta for torsion? Couldn't we say something like this? Could we have a virtual analysis, a real analysis, a material property, and a section property? Remember this from Engineering 216, that the angle of twist TL over GJ? Couldn't you do that? Yeah. Couldn't we do it for shear? We could do it for torsion. We could do it for anything, right? So if we wanted to generalize the principle of virtual work, like so far all we've considered is flexural deformations, but if we really wanted to get kind of nuts with it, we could do this, right? We could say, all right, what about axial deformations? What about shear deformations? What about torsional deformations? What about thermal elongation? What would happen if we took a structure and heated it up? How would the deformations respond there? Okay, and the idea is that what we would do when we would compute deflections is that we would only consider the terms that are relevant. Okay, like in reality, every structure deals with all of this, right? I don't care how well you fabricate that truss. No truss is fabricated such that all the centroids perfectly coincide. No truss is fabricated such that the loads are applied perfectly at the joints. There's always a little bit of eccentricity, there's always a little bit of friction, there's always a little bit of that, so there's always going to be a little bit of shear, a little bit of flexure, and so on and so forth. But we don't consider that in truss analysis because it's not that relevant, right? We just sort of disregard all that other stuff, even though it might actually be there. Does that make sense? We've never worried about torsional deformations, at least in the problems that we've done, because we never had any elements that are being twisted in most civil engineering structures. We really try and avoid that anyways. But the idea is that generally this is what virtual work looks like. Okay, so I guess my question is, what about a frame? Okay, well, frames could see all three. It could see axial loads, it could see moments, and they could see shears. Okay. Now, for our discussion and for what I am making you responsible for in CE 312, I'm not going to make you responsible for shear deformations. We're going to talk about them here in a little bit, but I'm not going to make you do that. But I am going to discuss them here in a little bit. But I do want to talk about frames, that frames do see both axial loads and flexure. Okay? And I want to show you what happens when we look at a frame problem and we consider both of these. We consider both axial deformations and we consider shear deformations. What we're going to find is that one of these is really important and one of them isn't. Okay? And the only way to show you is to just do the math and go through an example. Okay? So for now, we're not going to worry about shear deformations. We're only going to look at axial and flexural, but we'll look at that here in a little bit. I want to go through this example. This is a pretty simple frame. Okay, it's a pretty simple frame. And I want to determine the vertical deflection at point A. So we're only going to look at one deflection, because I think if you know how to do one, you know how to do them all. And we're going to investigate the deflection in this structure looking at both flexural deformations and then axial plus flexural. And you probably saw it on that slide, but axial deformations, as you're going to see, don't really matter all that much. Okay? For the members in this frame, I'm giving you some values, which I'm going to talk about these values here in a little bit. But I've got an element which is made out of maybe a high-grade steel because the E value is 30,000 KSI, and I'm giving you an A value of 4 square inches and an I value of 800 square inches. Now let me actually talk about those values here in a little bit. Okay, actually let's do it now. Okay, so area is, so the A value is a measure of axial stiffness, right? The bigger the A value, the more resistant to axial deformation the member is, right? If a member is stretching too much, you make the area bigger, right? Same thing with I. If the member is bending too much, make the I bigger, and it'll bend less. It'll deform less under flexion. Does that make sense? Now, I'm giving you an A value of 4 and an I value of 800, okay? So I propose to you that in real life, this beam would be very unrealistic, but the ratio of axial stiffness to flexural stiffness is very, very low. This beam has oodles of flexural stiffness and very little axial stiffness. So if I was going to try and make the point that axial deformations didn't matter, this would be the beam to do it because it's very flimsy axially, but it's very stiff flexurally. Okay? Let me paint the picture for you. How many of you all have a house or an apartment that has maybe a deck, right? And the floor beams, the joists, the wooden joists, they're sticking up like this, right? They're not like that, right? Because it's stiffer this way than it is this way, right? Now, why is it stiffer this way than it is this way? Well, it's stiffer this way because it has a higher moment of inertia this way, right? And I seem to remember that if I have a rectangle with B and H, that A is BH and I is BH cubed over 12, right? So the taller a beam gets, the stiffer it gets flexurally, right? Okay. So I did some math before class, and for this to work, for you to get a beam that has an area of 4 square inches and an I of 800, this is a really silly cross section because what it's got to look like is it has to be about 48.99 inches tall, but it's only 0.082 inches thick. That's stupid. That really is stupid. But I'm trying to make the point that if there's any beam that is going to have a ridiculous amount of flexural stiffness with a really small area, this is about as crazy as it could get, okay? And you'll see what I mean as we get into the example, okay? Everybody with me so far? All right. Okay, so what we're going to do is we're going to compute the vertical deflection at point A using these loads here shown and these values shown, okay? So what I'm going to do is I'm going to do a real analysis and a virtual analysis, and I'm going to do them side by side, okay? So my real analysis, let's see. Okay. So here's the real structure. All right. The real structure has, this is 10 kips. This is 20 kips. This is 3 kips per foot. That's 20. That's 10. Okay. And then, oh, that's A, B, and C. Okay. All right, by the way, while we're doing this, you tell me, are you okay if I just give you the reactions? Like at this point, can I just give them to you and can we all feel comfortable with being able to do it? Like if I told you that this vertical reaction was 70 kips, this horizontal reaction was 20 kips, and then we had a moment reaction of 600 foot kips. Is that okay? Everybody okay with that? Okay. All right. Okay. All right. Now, on the side, and I'm going to try and do these maybe a little bit in parallel. And I'm actually going to do something a little different for this problem. Let's put the virtual structure right here. And remember, we're looking at come on. Vertical displacement at A. So you all tell me, what do you think? A goes downward? Does that sound about right? Okay, let's see if that happens. I can't remember if it actually does or not. Okay. So okay. Would everybody agree with that? That that's going to be my virtual structure, kick off all the original loads, and put that on there, right? So these are the two structures I need to analyze, the real structure and the virtual structure. And likewise, are you all okay if I just say that this reaction here is 1, and then this moment reaction, I can do better than that, this moment reaction is 20. I'm getting technical with the units, it's 20 feet. Is everybody okay with that? Okay. All right. So, all right. So we need to do a real analysis and a virtual analysis, okay? Let's just sort of take stock of where we're at, and let's take stock of the rules and the tips and tricks that we talked about over the past couple of lectures. We said that it always makes sense typically to sum moments at the, free end? So maybe what I'll do, here's maybe what I'll do, is I'll have one coordinate system that sort of goes like that, starts at the free end, goes up the member. So maybe what I'll do is I'll cut a section like that, right? It doesn't matter if the axis goes left, right, up, and down, right? We'll just say that we're integrating from A to B, so from x1 equals 0 to x1 equals 10, right? And for this fixed end, like I don't really think this is going to work very well. Like I'd love to be able to use the free end, but I kind of think this is going to be complicated. So I think the only way that we're going to be able to do this, unfortunately, is to just go like that. And so we'll have another section cut, maybe something like this. I know that sucks, but I don't really think we can get around it. Okay? Now, would everybody agree, for instance, for member AB, we only need one moment function, and for member BC, we only need one moment function. Okay? So we're going to do the same thing over here, right? Whatever you do for the real structure, you need to do for the virtual structure. So we'll say, we'll cut the section like that, and then cut a section like that. Okay. So far, so good? Now, I'm going to do something a little different. I'm going to do the virtual structure first. Okay? So, let's do that. Let's do section 1-1. Now, I think it's going to be easiest to cut a section looking down. All right, bear with me. I'm going to throw that down a bit. Okay. So if I cut a section looking downward, okay, what do I got? Here's the section, right? there's 1. This is point A. This is where I cut the section. This distance is x1, right? Okay. So let's see if we can do this really easily. Move that up a little bit. All right. If I have 1 down, what's got to be going, what's the vertical? 1 up, right? So if I have an F, it's going to look something like that, right? Is everybody okay with this? Okay. So would you agree that F is 1? Would you agree with that? 1. And would that be valid from 0 to 10? What is, by the way, what's the moment in this member? 0. There is no moment in this member. This member's not being bent at all, right? So this is 0, from 0 to 10. Okay? Everybody okay with that? Because, I mean, if I sum moments at the cut, there are no forces generating any moment. So there's no moment right there. Okay? So if you're okay with that, I want you to follow with this over here. Now let's look over here. We're going to be engineers about this. Okay, so we're going to do the same thing. You go away. That messed me up. Here's my section cut. What do I have here? I've got a 10 kip load, a 20 kip load, right? This dimension here, we're going to call that x1. Same idea as we have over there. That's our free body, right? Okay. So would everybody agree I'm going to have a capital F? Okay. What is capital F?
10 kips.
10 kips. That's valid from 0 to 10. Okay. Everybody with me on that? Now watch this. Would everybody agree that I am going to have a moment? Now watch this. I'm going to say that it's, who cares? Who cares, of course, evaluated from 0 to 10. Now, come on. You're being stubborn with me. Why, by the way, am I saying who cares?
Because the virtual is 0.
Exactly. See, what am I going to do? I'm going to integrate little MAB times big MAB over EI, right? So it's going to be 0 times whatever this is from 0 to 10. It doesn't matter, right? It doesn't really matter what it is because I know that integral is going to give me 0. See what I'm doing here? So I just, it doesn't matter. So I did the virtual one first because I was sort of looking at the free body diagrams. I just went, well, this one's going to be easier. You know what I mean? Let's just do it, you know? So maybe what I'll do is I'll do the same thing. All right, maybe what I'll do is I'll do the same thing over here for the maybe I'll do the same thing for these. So So let's do section 2-2. We're going to look to the right. And we're going to do the same thing over here. If you'll permit me, in the absence of having to do all this scrolling up and down, which I know everybody loves, so I'll look up here once and then I'll just start drawing. So what I'm going to be doing is drawing this free body diagram and this free body diagram. So on the virtual structure, all I have are the reactions. For the real structure, I've got the reactions, but I've also got this distributed load. So let's see what we've got here. All right, so here on the virtual structure, what is going on? My tablet is not liking me right. Oh, all right, hold on, give me 1 second. I'm going to load this back up. I'm afraid my OneNote's starting to not like me right now for some reason. Okay. Behave. Okay, so here's the structure. We have a reaction over here, 1 and 20. I'm drawing those in red because on my free body diagram I know those. Okay, and I'm going to get, here's my structure here. And let's just think about this in a full unknown fashion. I'm going to have a shear, a moment, and an axial force. Now, I'm not using the shears now. I'm not using them, okay? So I mean, it's there, but I don't really care about it. Can somebody tell me what is F, and keep in mind this is point C over here. Oh, and I forgot my dimension. This dimension here is x2. Can somebody tell me what is FBC? 0. From 0 to 20. Now how about M? Maybe what I'll do for M, maybe I'll be a little bit on the formal side. Move that over there. All right. So I'm going to have M going like this. I'm going to have 1 times x2. And I'm going to have 20 like that. So M plus 20 is x2. X minus 20. Oh. But is that okay? Is that okay? Did I go too fast on that? I didn't go too fast? Okay. So now what we'll do is we'll sort of do the same thing over here. So we'll say, okay, here's our free body. There's our section cut. And so just like over here on the right, we have a shear, a moment, and an F. Okay? One of the things I'll tell you about virtual work, and this is particularly true with frames, is that So whenever you're writing these expressions, you know, we've gotten into the habit of adopting a specific sign convention, but what's really important is that whatever sign convention you use here, you use the same directions over here so that your assumptions match. So you want to be very cognizant of that. Okay, so over here we've got, this was 70. This was 20. That was 600 foot kips, and this is 3 kips per foot. Let me lower this just a tad. Okay, so that dimension is x2. Okay. So, before we start writing equations, what do I ought to do with this distributed load? Collapse it, right? What am I going to collapse it to? What is that?
3x over.
And from, we'll say from this end, we'll say x over 2, but in this case, here, I'll just do it like that. x2 over 2, right? Tell me if I'm going too fast. Is this comfortable? Okay. All right. So, what is FBC?
Minus 1.
It's minus 20, but I have a different answer. Why do I say that?
Because it's 0.
Because this is 0, right? It doesn't matter, right? So, I'll put the limit on it doesn't matter. Okay. So for the moment, we got a little bit more work to do. This one's going to be a little bit on the, I'll say the nastier side. So we will. So we're going to have M like that. What do we got? We've got 3x2 times x2 over 2. Like that. What else? What am I missing? Do we consider the 20 kips? Do we consider the 600?
Yes.
Yeah, we do need to put the 600 right here. And then we've got the 70 times x the other way. So therefore, how do we want to write this? Maybe we'll write it as 70x2 minus 1.5 x2 squared minus 600. Is that fair? Is that okay? If you understand that, then the rest of this problem is really just plug and chug. Okay. But I want to take a second. I don't want to rush because we got plenty of time. Everybody good? Okay. So okay, so we're going to use the method of virtual work. Okay, remember, that. Okay? So far, so good? All right, so here's how I'm going to do this. I'm going to say delta A flexural first. And then we'll do the axial terms later. So we'll deal with this part first, then we'll deal with this part. Okay? So, how do we do this? Well, it's we're going to be summing up those integrals, right? So, just to write it sort of formally, I'm going to factor out the EI and make sure I include my 1728. And then I'm going to have one integral from 0 to 10 and one integral from 0 to 20. But we already know that this integral right here goes to 0. And that integral goes to 0 because one of the functions was 0. We recognize that. We didn't even bother deriving the other one, right? So what we're going to have to do is evaluate the following function, or the following integral. Okay. All right. So I want to ask everybody, are we experienced enough with the tenets of definite integration that can I just give you this answer? I mean, because here's an integral, here's 1728, there's E and there's I. Would you all be fine if I just said that this is 3.36? Is everybody comfortable with that? So therefore, actually, here, let's just do this. Okay. So what I'm saying is that if all we were to do is consider the effects of flexural deformation, we would predict that this frame would deflect about 3.36 inches. Everybody with me on that? So what about the axial effects? Okay. Well, the axial effects, I'm going to predict this way. Now, some of you might be asking, well, wait a minute, why are you using this and not an integral? Because all the f terms are constant, right? Remember, if all the f terms are constant, if we have this whole term is constant, we have little f, big F, EA, times an integral from 0 to L of just dx. That integral is just L, right? So we don't need to perform the integral. We didn't have to do it for trusses, sort of the same thing here. So we're going to have little f, big F, L plus little f, big F, L each over EA. And I'm writing them each over EA. I mean, technically it's all one fraction, but if EA changes from member to member, you'd write it like that. And by the way, this fraction is 0 because that one force was 0. So all we've got to do is 1.0. This was 10 kips. This member is 10 feet. And then we have 30,000 KSI, 4 square inches. Anybody see a problem with this, by the way? What's the bottom units? KSI times inches squared. Kips times. Remember what we had to do in trusses? We had to convert the length into inches so that the units would yield an appropriate answer. What do you get when you chug this out, by the way? .16? You sure? Because on the bottom, I've got like 30,000 times 4, so it should be like a 12 something. And so a 12 on top, 12 on bottom should be like a 0.1 or something.
1,200 over 120,000.
So is that 0.01? You're shaking your head, So what does this mean? It means if we go through all the trouble to consider all those axial effects, our deflection only changes by 1/100 of an inch. And keep in mind, I was really stretching it to make a beam that's really flimsy axially. Axial stiffness is a lot crazier than you would think. So typically in frame analyses, we can just ignore the axial stiffness, and that's why. But I like this problem because it forces you to think about your strategy, like how we went the who cares. I kind of like this problem because of the who cares part. Okay. Let me take a step back. Anybody have any questions on this? Okay. All right. I want to talk a little bit about, to end our discussion on deflections, I want to talk a little bit about something. I want to talk about this. So notice how when I've been drawing beams, like here's a cantilevered beam. And I draw it kind of like this, okay? I don't do this. I haven't drawn very many cantilevered beams like that. Or a cantilevered beam that's like that. Let me ask you a question. Do you think these two beams would deflect the same way? Do you think they would behave the same way? They wouldn't, right? This is a very deep beam. This is a very slender beam, okay? So why am I bringing that up? Okay, well, the reason I'm bringing that up is because I want to talk about shear deformations. So shear deformations would be, so first off, how would you incorporate shear deformations? You would incorporate shear deformations the same way you would do this. Instead of a little m big M or a little f big F, there's a little v and a big V. So first off, like how do you do it? It's very easy. Okay, so how would you do it is you would just sum up the integrals of little b, big B, and then the material property is G, that's the shear modulus, you can look that up for any material, and then the section property is A. Now, whenever you formulate shear, and I'm not going to make y'all do this, but whenever you formulate shear, there's sort of an added section property gets thrown in, and you can derive what that section property is depending upon what your shape looks like, and we call that term K. but those are lookups, okay? So the way that you would do it is you would have a real shear function and you would have a virtual shear function. Same way we've been doing it this whole time. You would have the shear modulus, you would have the cross-sectional area, and then you'd have this, what we call a shear shape factor. And again, you can look this up. So if your beam is a rectangle, you can actually derive it, and K is 1.2. If your beam is a circle, you can derive it, and it's 10 over 9. I'm not going to make y'all do that. And then if you have an I shape or something with a sufficiently thin web, we just take K to be 1. Okay? Now, why do shear deformations matter? Shear deformations matter when the beam gets something like this. Something that was a little subtle in our derivation of beam deflections is that we assumed that the beam was inherently slender. Like when we look at beam deformations, we sort of assume beams are slender by their very nature. But that's not always the case in the real world. So a couple of examples whenever you have deep beams so one of them would be what's called a transfer beam. So like for example, how many of you have ever been in like a hotel with a really, really big lobby, right? And you go into the lobby and then you can see rooms, right? But the lobby stretches multiple floors. Well, there's gonna be this one beam that has to support the weight of like all the stories on top of it. And we call it a transfer beam. And that beam sees a lot of shear, right? So in order to make that beam work, it has to be really, really deep, okay? Another example of a deep beam is on a bridge, the pier cap, okay? I'm sure everybody has seen something like this, right? So when you're designing this component of it right here, you're sort of treating this like it's one big cantilevered beam. And it's got a load here and a load here. So this beam that I drew up here that looked kind of cartoonishly big, that's actually kind of what you're seeing right here. That's a really big beam, okay? So you do see it in the real world, okay? So the question is, do I need to consider shear deformations or not? I mean, in the last example, we were able to, I think we sort of realized that in the last example, we could ignore the axial deformations and it really wouldn't affect your answer that much. When do I as an engineer need to consider the shear deformations? Well, if I call this dimension L, and I call this dimension D, I propose that when the ratio of L over D gets around 10 or less than 10, you need to start considering shear deformations. Let me show you. All right, here's some numbers to consider. Okay, so I got a simply supported beam, uniformly distributed load. Okay, so we're going to take this as made of steel. So the Young's modulus for steel is 29,000 KSI, and then the shear modulus for steel is about 11,000, 1,200. We're going to look at shear deformations for this problem. Okay, so the way that we're going to calculate these deflections is we're going to have a flexural deformation, and we're going to have a shear deformation. Now, because we're going to use rolled I shapes, we're going to take K to be 1. And I went ahead and derived all your moment functions and your shear functions. You all could carry this out on your own if you wanted. Okay, so let me show you what happens. Let's say we use a W14 by 26. Remember what the 14 means? That's about how deep it is. Okay, so this is a 25-foot long beam that's about 14 inches deep. So if you calculate the L over D, it's 21.6. That's a pretty slender beam. Okay. Now for the area we're just taking the area of the web, just the part that resists shear. So that's the area, that's the moment of inertia. And so when you calculate all of this, for the flexure, you get this number, and for the shear, you get that number. So the ratio between the two, not that big of a deal. So if you're not considering shear, your answer is going to be off by about 2%. No big deal. But what if we make the beam deeper? What if we make it a 24 by 76? Okay, so the beam's a little deeper. Okay, the area and the moment of inertia go up, so the deflections as a whole go down. But when you compare these two, they're a little closer. Okay, and when you start crossing that L over D of 10 ratio, again, the deflection values, because the beam is just getting bigger, the deflection values are dropping. But what happens to the comparison between these two? Now you're starting to see some error, okay? So whenever you deal with a really, really deep beam, you need to consider shear deformations. Most software packages will tell you or ask you whether or not you want to turn that on or off. But that's what that means, is that when you're sort of considering when the beam behaves very, very deeply. Okay? Does that make sense? So, factoid for you. We'll see that in some mass stand stuff. That's all I got, everybody. Come with questions on Friday.